Hello everyone, I welcome you all. Let's quickly start solving this paper. Alright, so today we'll be solving paper 6, Probability and Statistics 2 of February March 2026. The paper is of 1 hour and 15 minutes. Let's see how quickly we can solve this. Right, moving forward, the first question comes from the topic of estimation, sample and estimations. So the height size centimeters of a random sample of 8 one-year-old plants of a certain variety were measured with the following results. Now, we're not going to go into the question first. We're going to first break down the question. The question says 8 one-year-old plants. So this is the sample size, right? Now, they've asked calculate unbiased estimates of the population mean and variance. Now, if you look at the formula table of MF19, you'll find that you have different formulas. Almost all formulas are mentioned, except for some which you have to memorize. That will go on later to the paper. So, we have ungrouped data, right? So, we'll be using this formula to calculate the sample mean. This symbol x bar is called sample mean. This is summation of the data, and this is your sample size, the maximum number of samples that you've taken, which in our case over here is 8. Now, moving forward, so copy down the formula, although this does not have any marks, but I'm doing it for the viewers so that you may remember this formula. All right, adding up all of these numbers will get the number 841 divided by n. Solving this further, you can do that in your calculator while we're solving the paper. It helps to get used to the calculator. The exact answer is coming out to be 105.125, or if we round it off to 3 significant figures, that's what is required. That is 105, right? Now, if we look for the variance, we know, or if you don't know, variance, you guys should know, is the standard deviation squared. If you look at the formula, you will only find formulas for standard deviation. And in this case, we have two formulas here, right? Obviously, we're going to use this one. This is the less complicated one. This just means that all of the individual values that we are trying to find out, 104, 96, we are just squaring it. All right. So the square of 104 would be, just whip up the calculator again. So 104 squared would be 10,816. 96 squared would be 9,216. 110 squared would be 12,100. 122 squared would be 14,884. 96 squared would be again 9216 as mentioned before. Then we have 101 squared, which would be 10,201. Then we have 99 squared, 9,801. And then we have 113 squared, 12,769. Now, when we add up all of these, sigma x square, that's what sigma x square means. We get the value 89,003. Right? Now, plugging it into the formula is, especially for variance, if you look at it, it's basically just under root sigma x square upon n minus the sample mean x bar, right? So when we square it, this cancels out. We are left with 89,003 divided by 8 minus n. Remember to always use the exact value, right? So we are going to use 841 upon n, the whole thing squared, right? This is the formula. I forgot to mention. You plugging this into the calculator, we'll get 84.7, or we'll get the fraction 4743 upon 56. All right, this is our final answer. Either is the final answer. All right, then moving on to part 2. It is now given that the true value of the population variance is 85.0. All right, so they've given us the exactly true value, which is 85.0. Stating a necessary assumption, find a 99% confidence interval for the population mean of h. H is basically the population, as they mentioned in the previous part, giving the limits of the interval correct one decimal place. All right, it's a relatively simple question. Let's move on to solving this. Now, the important thing to remember here is that there is a formula that is not mentioned regarding this in the MF19, and that is the formula that you need to remember. All right, so basically, let's break this down. So we have the new population variance as 85.0. All right, that is clear. Stating a necessary assumption, find a 99% confidence interval. Basically, what this means here is that if we were to draw the normal distribution graph, right, and we know that the mean value is 0 over here, they want us to find out, or rather, confidence interval means that, as in the name confidence, you are 99% confident that your answer, whatever answer is, it will lie in between this range, and that is the range that we're trying to find out, right? So moving forward, it says here that we need to find a 99% confidence interval for the population mean. As it says population the confidence interval, that means we need to find two values. One is your positive z value and one is your negative z value, right? And this has to be 99% or 0.99. Now, if you were to check, okay, what is the percentage left? That is 1%. If we divide by 2, we'd be getting 0.05 over here and 0.05 over here as well. Now, moving forward, you guys need to remember the formula for confidence interval, and that is sigma x over n plus minus z value multiplied by the under root of the standard deviation square, in which case over here it is our variance, right? Standard deviation squared is just variance divided by the sample size. Now, before we move on, we need to find out the z value corresponding to 0.99% confidence interval. But we need to make sure, always remember that whenever we are finding out the z value, we always we find out towards the left of this, of the value, right? So whatever probability we get is towards the left hand side of that, and if you check that out, that is basically just 0.99 plus 0.05. So most students make this mistake that they always find out the z value corresponding to 0.99, but but they need to make sure that the value over here, they're also factoring that in. So we are going to be finding out the z value for the probability of 0.995. Now, if we move on, all right, so if we move on to the table, the z value for 0.995 is 2.576, right? So 2.576. Solving this further, we get sigma x, if I remember correctly, was 841 divided by 8. Then we have plus minus 2.576 into under root of the new population variance that they've given, 85.0 divided by n, which is 8 over here. Now, if you were to plug this into the equation, you would get the, what do we call it? The lower value you'll be getting as 96.7, and the upper value you will be getting as 113.5, and that will be your final answer. Now, let's move on to question number 2. Question 2 says that last year the time in minutes spent by customers in a certain shop had mean 10.5 and standard deviation 6.8. So they've already given you the mean and the standard deviation. This year the shop owner wants to test whether the mean time spent by customers has changed. All right, he decides to choose a sample of 20 customers. This is going to be your n. Let's see whether this continues being n or not. Let's move forward. This is typically going to be a hypothesis testing question. So let's move forward. A shop assistant suggests that they should choose the first 20 customers who enter the shop one morning. They're asking for give 2 reasons why this will not produce a random sample. Now, in your mind, you should think of this as you are standing in the shop and you are choosing the first 20 customers that walk into your shop, right? Now imagine this. It's early morning. It's not the bustling time of the day. So that is not your typical of all times of day, right? So one reason here is that that is not a typical time for customers. Another reason could be that a shop assistant suggests that they would choose the first 20 customers who enter the shop one morning, right? So that is only one morning. They are not choosing it over a span of many days. Therefore, it is not a typical day as well. They're only going to be basing their assumption on one day. That's not how data should be. Data should be unbiased and it should have plenty of, it should basically cater to very erroneous variables as well, right? So not typical days as well. Other reasons could have been, you could have written this, not, it's not necessary that this is not your typical what do we call it, specific answer. There could be multiple answers to this question. One answer could have been that customers may arrive in pairs, or they could have arrived in groups, meaning specific groups are, they are not independent to each other, they are dependent upon each other entering. And you could also have written that there is biasness in the data as well. But this is, these two solutions will get you full marks for the question. Now, moving ahead, the shop owner decides to carry out the test at the 10% significance level. He chooses a random sample of 20 customers and he finds that the mean time spent in the shop by these customers is 8.4 minutes. Now, if you look above last time, the time in minutes spent by customers in a certain shop had mean 10.5, right? And the standard deviation was 6.8. Now, if you look closely, what was the actual mean? The actual mean time was 8.4 minutes, and that is what you are testing against. You are testing whether the time spent by customers has changed. Now, another important keyword over here is changed. Since they have not mentioned whether it has increased, whether it has decreased, so you'll see why further when we move on to the question. That is important, right? For now, let's attempt the question that they've asked. State an assumption that is necessary for the test. If you mention here, if you see here carefully, that since they mentioned the mean and the standard deviation, so we are automatically going to assume that this is normally distributed, right? However, you need to make one thing sure over here is that they have not mentioned any change in the standard deviation. So that is one assumption that you're going to make over here, that you are going to assume that the standard deviation is unchanged. Assume standard deviation has changed, right? Or you could have also said that the standard deviation equals to 6.8. Now, let's carry out the test. Now, there are certain steps that you need to follow for carrying out the test, and that is firstly, H naught. H naught is basically the the unchanged hypothesis H naught, where your population mean time, in this case, the population mean time, meaning the time that customers spent in the shop, as they've stated here, is 10.5 originally. That's what they calculated before, right? So that is 10.5. Now, the new hypothesis, or the hypothesis that you're stating over here, wherein you have to mention the change, that is going to be the population mean time. Now, here comes the important part. Since they've mentioned changed, they have not mentioned whether it has increased or decreased. If they would have mentioned that it has increased, therefore we would have put a greater than sign, 10.5. But since they have not mentioned that, or if they would have mentioned that it is less than, so we would have put a less than sign. But since they've mentioned that it is changed, they've not specifically mentioned increased or decreased, therefore we'll be adding a not equal to sign, 10.5, and therefore this will be a two-tailed test, right? Now, moving forward, the second part of the question, obviously, is that we need to find out the whether the test has failed or not. So firstly, we need to make sure that significance at the 10% level, right? Now you could use either of the two. Since it's a two-tailed test, you can test on both sides of the extreme. But first we need to make sure that what is our boundary, right? So if we look at the boundary, they're asking for 10%, which in this case would be 0.9 for positive. Let's find out what is the positive value for the z value, right? So if this would be 0.1 or 10%, we need to find out the z value for 0.9. Let's look at the z table. If we look at the z table, so what have they mentioned? Carry out the test at the 10% significance level. He chooses a random sample of 20 customers. Right. So if we look at the z table, 0.9, 0.9, searching for 0.9. Right. One thing that I forgot to mention here was since this is a two-tailed test, so that means our actual significance level is going to be at 0.05, right? So that means the probability over here will also be 0.05. And what we're actually finding out, as stated earlier, was that whatever your z value is, it is towards the left hand side. Therefore, again, in this case, we will be looking for the z value of 0.09 plus 0.05. So if we look at the z table over here, we'll be finding out the value for 0.95, right? So that would just be 0.95, and the z value for 0.95 over here is 1.645. Now considering this, our z value is 1.645 over here, and for this it would be negative 1.645, since we know that the normal distribution table is a mirror image of each other. Now moving forward, let's look at how to solve this. So as we know, the formula for z is just going to be x minus the mean over the standard deviation under root of the variance, right? But the important thing, or under root of the standard deviation, but the important thing here is that in hypothesis testing, the formula is a bit changed. The formula basically becomes for the z value, or rather for the testing value, or you could say the test statistic, that is the actual value that we compare our answer against. That would be the new mean 8.4 minus the old mean, which is 10.5, upon, if you look closely, we have the standard deviation divided by the under root of the sample size. This is basically the formula for that. And if we look closely, we solve it on our calculator, we get the value for negative 1.381. Right now, negative 1.381 is going to be lying somewhere over here, right? Negative 1.381. So that is greater than negative 1.645. It does not lie in the what do we call it, significance level. It does not lie under the significance level. So therefore we need to state that negative 1.381 is greater than negative 1.645, right? Therefore the final answer that we'll give has to be contextual. So we will be writing there is insufficient evidence that the mean time has changed. Alright, and therefore you could have also written that we will not be rejecting the original hypothesis, or H naught. All right, moving forward. Question number 3. A shop sells two types of cell phone. Sales of the two types occur at a constant average rate. Now, immediately, whenever you read the word constant average rate, one thing that should pop up in your mind is that this is a Poisson distribution. All right, Poisson distribution, which will have, as it says further, of 3.2 per week of for one type and 2.9 per week for the other type. Right, so we can state this here that sells two types of cell phone. Sales of two types occur at a constant average rate for one type. All right, so we can say that type 1 follows Poisson distribution with lambda or mean 3.2. Similarly, type 2 follows Poisson distribution as well with mean or lambda 2.9 per week. Right, now let's move ahead. You may assume that sales occur at random independently of one another. Obviously, a week is chosen at random. All right, find the probability that the shop sells a total of 5 cell phones. Whenever you have the word total in your question, only one thing should come in your mind, that you are going to add both of the means or you are going to add both of the lambdas together. Right, so this will just become 3.2 plus 2.9, which adds up to your Poisson distribution being 6.1. Right, now if you move on to the MF19 table, you'll find out that you have a formula for Poisson distribution, and that is e to the power of minus lambda to the power of r upon r factorial. Now you must be wondering what are each of these things. First, let's copy down the the formula. So the formula is e to the power of minus lambda times lambda to the power of r upon r factorial. Now they have asked us for a total of 5 cell phones. 5 over here is your value of r. So they've asked us for the probability of x equaling 5. That will just be e to the power of, as we know, lambda is what's in the bracket, so that will be negative 6.1 times lambda itself, 6.1 to the power of 5, because that is the value of r upon 5 factorial. That's it. It's just plug and play in this part. And if you plug it into the equation in the calculator, what you'll find is that you'll get 0.158. That's your final answer. Moving on to the second part. Find the probability that the shop sells exactly 5 phones of one type and none of the other type. Now, whenever you have a scenario, I need you a scenario like this where they're asking you to where basically you can make cases. I would suggest that you make cases over here. Right, so if we see here, we have two types of phones, type 1 and type 2, and they've asked find out the probability that the shop sells exactly 5 phones of one type and none of the other type, and they've not specified which type should sell 5 phones, right? So in that case, we can assume that in one sale or in 1 week, 5 phones of type 1 were sold and 0 phones of type 2 were sold. Similarly, it is also entirely possible that in another week you have 0 phones of type 1 being sold and 5 phones of type 2 being sold, and these are the two scenarios or the two cases that we need to solve for, right? So solving for the first one, we know that the Poisson or the lambda for type 1 was, if we look above, that was 3.2, right? And for type 2 that was 2.9. Right, now solving this further, we have e to the power of minus lambda, which is negative 3.2, and in this case for type 1 we have 5 phones being sold, therefore 3.2 to the power of 5 divided by what do we have here, 5 lambda multiplied by e to the power of negative 2.9 multiplied by 2.9 to the power of 0 divided by 0 factorial. Now anything to the power of 0 will automatically be 1, and therefore if you put in your calculator, 0 factorial is also 1. Now considering the second case, let's move on to the second case where we have 0 of type 1 and 5 phones of type 2. Now in this, your equation will obviously become e to the power of negative 3.2, and as stated earlier, anything to the power of 0 and divided by 0 factorial will just be 1. We will be multiplying this e to the power of negative 2.9 multiplied by what do we have here, 5 of this, so 2.9 to the power of 5 divided by 5 factorial. Now, the answer for the first part we are getting is 0.0062715, and the answer for the second part that we're getting is 0.0038336, right? So if you add all of these together, and we also make sure that we're giving the final answer correct to three significant figures, the final answer comes out to 0.0101, and that is your final answer. All right, moving forward, we have B part 1, where they now say use a suitable approximating distribution to find the probability that the shop sells a total of more than 30 cell phones in 6 randomly chosen weeks. Now, basically in statistics 2, there are only two approximating distribution that we study. One is from binomial to Poisson, right? Another is from Poisson to normal. Both have different criteria. So first let's see what, let me write down the criteria for both. Over here, your n value has to be greater than 50 and the probability of success has to be less than 0.1. Over here, just the value of lambda has to be greater than 15. This is the thing that you need to remember for both of these approximating distributions. Now, moving forward, if you see that the shop sells a total of more than 30 cell phones in 6 randomly chosen weeks. Now, they have chosen 6 randomly chosen weeks. And have they mentioned? No, they've said that they need a total of more than 30 phones. Now, if we look at the above question, the total follows Poisson distribution with mean or lambda being 6.1, but that is for 1 week. Since we have 6 weeks, so if for 1 week we have 6.1, then for 6 weeks, how many will be? It's simple math, simple cross multiplication. I think the answer will be coming out to 6 into 6.1, that is 36.6. So the total we are getting for the new Poisson distribution is 36.6 for 6 weeks. This is something that you need to do whenever they have given you more than, basically you have to just fill out the entire space. If for 1 week you know that you have 6.1 total sales being sold, total phones being sold, then for 6 months how many phones will be sold? You need to find out the mean value, and that is 36.6, right? So as we know that our lambda is greater than 15, and therefore this will be converted to normal distribution, where we have over here, once it will be normally distributed, remember one thing, that for Poisson distribution, whatever your lambda is, that will be the mean value, as well as lambda is your variance as well. For this specific distribution, your variance is 0. Therefore, once we convert this to normal, we get the value of 36.6 as the mean and 36.6 for the variance as well, right? Then we use the generic formula for the z value, which is z equals to x minus the mean divided by the under root of the variance. So that would be standard deviation squared. Now, following this value we have over here. Okay, so they've asked for the probability of x greater than 30. Now, when we need to convert this to the z value, we get z greater than 30 minus 36.6 divided by the under root of 36.6. The z value that we are getting over here is z value is greater than negative 1.008. All right, now let's draw the table over here. If we draw the table, so we need to find out the value of greater than negative 1.008. Negative 1.008 will lie somewhere over here, negative 1.008, and we need to find out the probability of greater than this, so this region that I've highlighted over here. Now, if you look in the table, you'll find out the z table, you'll find out that there are no negative values, so you must be puzzled as to what to do. What should we do now? So do not fret. The normal distribution table has one distinct property, and that is that it is a mirror image of itself, right? So if we look carefully, over here, and if we just mirror this, so we can find out the value of less than 1.008, and that would just be the phi of, we just need to find out, oh right, so we need to find out the value of the probability of greater than negative 1.008, and that would just be, this will just equal to the phi of 1.008. So let's find that out. Now 1.00, right, this is the value, 0.8413. And if we look at the eighth column, we'll be adding 19 to this. So adding this, we get 0. Okay, let's see here, we get 0.8432. This is 12. So yeah, 0.8432, and the final answer should be given correct to 3 significant figure, therefore 0.843 is your final answer. All right, now as they've asked here that we need to justify our approximating distribution, which we've already justified above, all you need to do is state that your lambda is greater than 15, therefore 36.6 is greater than 15. That's it. All right, now moving forward, they've asked the weekly sales X and Y of two types of computer have the distribution X follows Poisson distribution lambda and Y follows Poisson distribution mu. Basically, mu is the name of this variable over here, which stands for mu. Given that, now they've given us the equation. Over here, and we just need to find out an expression for lambda in terms of mu. We need to do nothing over here. We just need to make lambda the subject, right? Now, they have said x equals to 0. As we know, the formula here is e to the power of minus lambda times lambda to the power of r upon r factorial, and anything to the power of 0 divided by 0 factorial is just going to be 1. So that will be e to the power of minus lambda times 1 equals to 2 times, now here is where we'll use the formula, mu to the power, that would be 2 times e to the power of minus mu times mu to the power of 1 upon 1 factorial. Now 1 factorial is just 1, so simplifying this equation, we get e to the power of minus lambda equals to 2 mu e to the power of minus mu, right? Now simplifying this, will be taking logs on both sides, or rather I like to use natural logarithm, so taking ln on both sides. We have over here ln of e minus lambda equals to 2 mu ln of e minus mu. Now this will cancel out and these will cancel out, the powers will come down, so minus lambda equals to 2 mu minus mu, right? So right, yep, my bad. Simplifying the formula again, e to the power of minus lambda equals to 2 times e to the power of minus mu times mu upon 1 times just mu. So applying ln on both sides, we'll get e to the power of minus lambda equals to ln of 2e minus, or rather I should just put mu together, times e to the power of minus mu. Solving this further, this will cancel out and this power will come down here. We'll be getting minus lambda equals to ln of 2 mu plus ln e of minus mu. And if we solve this further, we'll get minus lambda equals to ln of 2 mu, this will cancel out, minus mu, right? And lambda would then equal to, just flip the equation, we'll be getting mu minus ln of 2 mu, and that will be your final equation. Now if you want, you can also write it in a more expanded form. Lambda equals to mu minus ln of 2 and minus ln of mu. All right, this is the basic indices rule, where ln, if you have two things being multiplied in logarithm, for example 5x, you can just write it as ln of 5 plus ln of x, right? Now moving forward, a firm sells cheese in packets. The mass of cheese in the packets is normally distributed with mean 1.12 kilograms and standard deviation 0.15 kilograms. The firm makes a profit of $0.32 per kilogram of cheese sold. Find the probability that the total profit made on 50 randomly chosen packets of cheese is less than $18. Now, this is basically the formula of linear combination of random variables. Right. And a firm sells cheese in packets. The mass of cheese in the packets is normally distributed with mean 1.12 kilograms. All right. So cheese follows normal distribution with mean 1.12 kilograms and standard deviation being 0.15 kilograms. The firm makes a profit of $0.32 per kilogram of cheese sold. Find the probability that the total profit made on 50 randomly chosen packets of cheese is less than $18. So we need to find the probability that the total profit made on 50 randomly chosen cheese. So basically this would just be 50C is less than $18. Right, now we need to make sure here that this is in kilograms and this is in dollars, so we need to convert that, right? So to factor in for that, we know that per kilogram they make $0.32, so this should be less than $18, right? Now what, usually calculating the expected value and the variance is of no issue, but the main issue comes with the variance, whether we need to square some values or not, and that's what we'll make sure here. All right, so if we look into the equation over here, we have the expected value of this of 50C times 0.32 would just be what do we call here, 50 times 1.12, that is the expected value, times 0.32, right? And if we calculate that out in the calculator, what we will be getting here is 17.92. now here comes the main part, which is the variance of 50C times 0.32. now you must be wondering, why am I writing this as times? The reason for me writing this as being multiplied by 0.32 is that 0.32 is the value that will be squared along with the standard deviation itself. 50 will not be squared. The reason being here is that they have asked us to find out 50 randomly chosen packets of cheese. They basically said that what you need to do here is that you need to add C plus C plus C plus C all the way till you have 50C, and then you need to multiply that by 0.32. And whatever we multiply, whenever we are multiplying things, those are the things that we square. Whatever is being added, we never square it in variance. So therefore the value we get over here is 50 is not being squared, multiplied by 0.15 squared, and that being multiplied by 0.32 squared, right? And the value that you get for that is 0.1152. Right, so your new distribution for the total population has come out to be 17.92 being your mean and 0.1152 being your variance. We need to find out the probability that the total was less than $18, right? So just applying the z formula that we learned earlier, the z formula being x minus the mu over the standard deviation under root of the standard deviation, under root of the variance, my bad, that would just be 18.00 minus 17.92 divided by under root of 0.1152, right? So this is the z value that we are getting. The z value that we are getting is, write it out, that would be 0.2357, and any probability less than a positive number would just be equal to phi of 0.2357. Let's find it out. So 0. What are the values? 0.2357, 0.2357 means 6, so 0.5910, and at the sixth value we are getting 23, so this would just be 0.5933. all right, and 0.5933 correct to three significant figures, this would be 0.593, and that is your final answer. Now moving on to the next question, question number 5. Now Anita has a dice with sides numbered 1, 2, 3, 4, 5, 6. The score on one throw is generated by x. Assuming that the dice is fair, show that the variance x equals to 35 upon 12. Now this again, we move back, formulas are given to us. This is basic, just for summary statistics. Again, we have ungrouped data over here. So what we need to find out here, we need to use this formula over here, and before that we need to find out the sample mean as well. So let's do that. We know that x bar equals to sigma x upon n. So first let's find that out. So that would just be 1, 2, 3, 4, 5, 6. The value that we are getting would be 1 plus 2 plus 3. 1 plus 2 plus 3, that's 6, plus 4 plus 5 plus 6, that would just be 21. So 21 divided by the score on one throw is generated by x. Assuming that the dice is fair, show that variance x equals to this. So 1, 2, 3, 4, 5, 6 divided by 6. 21 divided by 6, that would just be 3.5. Now we know the formula for the variance. Formula for the variance is just sigma x square upon n minus x bar the whole thing square, right? We just remove the under root from the standard deviation and it will convert into variance, as we did earlier as well. Now what the important thing that we need to do here is that the variance of x would equal to 1 square plus 2 square plus 3 square plus 4 square plus 5 square plus 6 square divided by n, which is 6 minus 3.5 the whole thing square. Plugging all of that into the calculator, which I've already done over here, is we would be getting what do we call 91 upon 6 minus I guess the fraction for that was 49 upon 4, and solving this further we get 35 upon 12 as our final answer. Right, now moving forward, Anita suspects that the dice is not fair. She thinks that low scores are more likely than high scores. She intends to throw the dice 50 times, and if the mean score is less than 3, she will conclude that the dice is not fair. Now which question is this? It's basically, it's not hypothesis testing, but it's kind similarly like that, but we're just testing we're just testing whether the dice is fair or not. It is now given that the dice is not fair. Okay, and the expected value of x equals to 2.5. Assuming that variance of x equals to 35.2 upon 12, calculate the probability of a type 2 error. You may assume that a continuity correction is not needed. All right. So before we conclude that, what is a type? I think we should answer types. Question number C first. State what is meant by a type 2 error in this context. Basically, type 2 means type 2 error is when you prove something is there when it is not actually there. For example, in this context, we need to conclude that the dice is fair when it is not. Concluding type 2 error would be when the actual truth is something else, but you've concluded it as something else. That is it when you make a type 2 error. Now, in this case, it would be, since they've already stated that the dice is unfair, so they've all done the thinking part for us. We just need to state what a type 2 error is. Type 2 error is proving something is not, proving something is true when it is not true, right? For example, if someone asks me to go get yogurt for them, and I did not go get yogurt, I just ordered that yogurt for me, and if we would calculate that probability, so that would be a type 2 error. I did not go, even though it may seem like to that person that I went and bought that yogurt, when that is not the truth. So over here, concluding that the dice is fair when it is not fair, that would be a type 2 error, right? Now let's solve this question. All right, now always remember here that whatever the true value we feel like, since they've already given us the final assumption, which is that the dice is not fair, that is what we'll be comparing our value against, right? So she says here, if the mean score is less than 3, she will conclude that the dice is not fair. And we need to make sure, we need to find out that we've done this error. We need to calculate the probability of a type 2 error, and in that we always make sure that it is the older mean minus the newer mean. If we go up in the hypothesis testing question, what we did here was we calculated over here the newer mean minus the older mean. When we're making a type 2 error, we are basically doing the opposite, right? We're finding out falsehood, or we are finding out things that are not true. So we need to find out that error, and in doing so, that will always be the old mean minus the new mean, right? So the old mean is 3 minus the new mean, which is 2.5, upon what we have over here is the variance upon the sample mean. So the variance calculated was 35 divided by 12, and the sample mean we have over here is 50. So let's plug that into the calculator. And the value for that, and the z value that we're getting basically is z value equals to 2.070, right? And since they've graciously mentioned that continuity correction is not needed, that is why we took the value of 3. So z value less than 2.070, sorry, my bad, since it's a type 2 error, this would be greater than that. So z value greater than 2.070. Concluding this further, we know that that would be 1 minus the phi of 2.070. So let's find out the value of 2.070. So we have over here 2.0, 0.9808, 070. So that is our final answer. So the final answer will be 1 minus 0.9808, and our final answer is coming out to be as 0.0192. Right, moving forward, the sample mean score from Anita's 50 throws of the dice was 2.9. Explain why it is not possible for Anita to make a type 2 error. So the only possible reason that Anita would not make a type 2 error is if her value, or if her test statistic, or if her score is in the critical region. right? So if her score of 2.9 is in the critical region, only then will she not make a type 2 error. And you could have also have written that the null hypothesis was rejected, or basically H naught was rejected, right? Now moving on to the last question. The question here says that the widths x centimeters of the stone found on a certain beach are modeled by the probability density function given by this value. Very simple, where k and where k and a are constants. Show that k equals to 6 upon a cube. Now, what we know over here is that if we were to integrate the probability density function in the limits that we are given, that is always equal to 1. The area under the graph is always going to be equal to 1. Therefore, let's do it for this. K 0 to a ax minus x square dot dx, we know that this will always be equal to 1. All right, so let's integrate this. This will just be ax square upon 2 minus x cube upon 3. The limits are 0 and a, and this will be equal to 1. Since we have limits, therefore no need for the integration constant. Now solving this further, let's plug in the values. So we have over here a into a square divided by 2 minus a cube upon 3, and obviously we have over here 0, so everything will be turned to 0 here, equals to 1. This will just be k equals to the final answer that we get here is a cube upon 6 equals to 1. Therefore, solving this further, we get k equals to 6 upon a cube. Right? Now, moving further, without calculation, give an expression for the expected value of x in terms of a. Give an expression for expected value of x in terms of a. So that is quite simple. Let me just explain this to you graphically so you'll understand. So a probability density function is nothing in the sense that before that the value is 0, and after that specific value of a, the value is always 0. So it starts from here 0, it goes all the way from here to here, and then it reaches 0 again. So the expected value is basically 50% of that value, and that is just going to be at the halfway mark, which is a divided by 2. Therefore the final answer in terms of a would be a divided by 2. Moving further, we have find the probability that x is less than 1.4a, showing that this probability is independent of a. All right, so what is the way that we can show this? They've given us the lower limit of 0, and they've also told a upon 4. So let's see this independent of a by integrating this entirely, right? So that would be k from 0 1 upon 4a. What was the equation? The equation was ax minus x square. So let's take this down further. This would be k 0 1 upon 4a ax minus x squared dot dx. Now we don't know the value for that, so we're finding it out. This would just be, as we can just copy it down from above, so that would be ax squared upon 2 minus x cube upon 3, 0 to 1 upon 4a. Since we know that plugging in 0 will just get 0, so we just need to plug in a upon 4. So let's see what that value gives us. One more thing that we have over here is, which I forgot to add, we have the value of k, which is just 6 upon a cube, right? That will help us, I think. Moving forward, this would be 6 upon a cube, a into 1 by 4a square, 1 by 4a square upon 2 minus 1 by 4a cubed upon 3. All right. So 6 upon a cube, that will just be, okay, so what do we have here? We have over here a upon 2. A times, this would just be 1 upon 16, right? 4 square 16, 16 into 2 is 32. So 32 right. So a will come up over here, we'll have a square over here, and we'll have 32 over here, minus we'll have 4 cubed. 4 cubed is 64, and 64 times 3 is 192. So then we'll have over here a cube upon 192, right? All right, so apparently what we have over here is that if we take a cube common, then our a's are cancelling out, and we have an independent value of exactly, let me put this directly into the calculator. So first let's simplify this. So this is 6 into 1 upon 32 minus 1 upon 192, which will just give us simplified value is 5 upon 30, sorry, 5 upon 32, or the exact value is 0.156, which is independent of a, and that we have proven. All right, use your answer to 6c part 1 to find the probability of 1.4ax to 3 upon 4a. All right, so this is quite simple, as I've stated above, that we can just use the graph to solve this, right? So this is 0 and this is a. The graph before that will just be 0, the graph till a will be a 1, and the graph after that will be again 0. So what do we know here? We know that 1/4 of a, the area under that, is just going to be 0.156. This value is 0.156. Similarly, if we were to find out the area from 3 upon 4a to a, that would also be the same as 0.156. So if we need to find out that area below, we just need to do 1, which is the total area, minus 2 times 0.156, or rather I should use the exact value, which is 5 upon 32. And let's plug this in the calculator and let's see what value we are getting. So the value that we're getting, or the exact value, is 0.6875, or correct to 3 significant figures, 0.688. All right, and that is the end of the paper.